All right, so two sets problem from the CSES problem set. So here the task is that we have the numbers from 1 up until n for a given n, and we have to split them into two groups essentially, or two sets if you will, which have equal sums. Okay. So what the request is that we output yes if the division is possible and no otherwise. And after this, if the division is possible, we have to print the example. So let's look at the sample case here. So for 7, he outputs yes, and then goes on to output the two sets. So 4 dictates how many elements we have in the first set. So 4 elements here, and this 3 here shows that we have 3 elements in the second set. So in the first set, if we add all of the numbers together, we will see that the sum is equal to 14, and the same goes for the second set. So this is a correct answer. It doesn't, in the task description, it doesn't say that we have to output a specific distribution of the elements. Okay. So for this test case here, where n equals to 7, we could have 1, 2, 5 instead of 4, and 6 instead of 7, and then the sum would be 14. And then in the second one, we could have 3, 4 instead of 5, and 7 instead of 6, and again the sum would be 14. Okay, so there is no specification about having like a preferred way of making this distribution of elements, right? And for the second example, n equals to 6, and since it is not possible, the output is no. And if we look at the constraints here, n goes up until to 1 million, so 10 to the power of 6 equals to 1 million, and that is a small number. So a linear solution, so ON solution, would be passing through this 1 second limit we have here. Okay, so let's go ahead and look at the solution here. Okay, so what I did here is I read n, okay, and then I calculate the sum that the range between 1 and n inclusive has. Okay, so this is the formula essentially, n times n plus 1. And then we divide this value by 2. So this is the sum formula. And this is just a simple application of that formula. And here, we just test that this sum, modulo 2, should be equal to 0. So if it is equal to 1, this will be true. And because the sum will be odd, we will just output no and return. Okay. So if we have an odd sum, and we're working with integers, it is not possible to split the sum into two sets, because then we would need real values. Okay, the 0.5 would need real values, and we don't have real values, we have integers, so it is not possible in this case. In any other case where the sum is divisible by 2, it is actually possible. Okay, so we just output yes, and then I just have two vectors here, vector A and vector B, for the first set and for the second set. And now the strategy I'm following here when distributing numbers is that they have two indexes. The first index shows to the first number, and the last index shows to the last number. Okay, and then I'm gonna follow a simple strategy here, which I will explain later. But before I do that, for the case where n is odd, okay, so n modulus 2 evaluates to 1, so this statement evaluates as true, I will do this. I will do this 3 actions here. So I will push I will push to set A 1 and 2. Okay, so numbers 1 and 2 will be pushed to the first set, and that means that the first set now has a sum of 3. And the other action here, the third action, is that I push number 3 to set B. So again, set B will also have a sum of 3. Okay. Now here in the comments I have some observations here, which will allow us to understand why I do that. So we know that n minus 3 is even, right? I will also prove to you at the end of the video why n minus 3 divided by 2 is also even, given that the sum is also is even, okay? So that if we reach this point in our program's execution, it means that we haven't returned from here. So the sum will be actually even, okay? And yeah, so this I will prove at the end of the video, why n minus 3 divided by 2 is also even. Sum minus 6 will also be divisible by 2 because sum is already even. So minus 6, which is an even number, will give us an even number, okay? So this is divisible by 2 again. And the strategy is, as I described here, that we take the first and the last element every time. And these will have the same value for every pair, okay? So if we take, let's look at the case where n is even, okay? If we take the first element being 1 and the last element being n, n plus 1 will be the result of the addition of these two elements, okay? After we, for the second element and for the second from the last element, so n minus 1 and 2 in this case, the result again will be n plus 1. So the pairs will have equal values, okay? If we always take the first and the last element. And eventually the two sets, as I say here, will have equal sums, okay? So if we keep creating the sets in this way by taking the first and the last element and putting it into the first set, and alternately doing this action every time, we will end up having the same sum in our sets. Here, for the case where the n is odd, because I have used already 1, 2, and 3 to make the two sets have equal values, okay, while managing to have now an even amount of pairs, okay. The first number will obviously be 4, okay, because it's the next number that comes after 1, 2, and 3, okay. So that's the actions I take when n is odd. Otherwise, I just go through the strategy that I just explained. So I have my, as long as first is less than last, okay, I alternatively push into the two sets. So this if statement here, if first modulo 2, it will manage to make it so that I go when first equals to an odd number, then we will push to the first set. When first equals to an even number instead, we will push to the second set, okay? So this manages to make us alternately push into each set, okay? And after we have pushed the first and the last element to that set, we're gonna increase first, and we're gonna decrease last, okay? Because we have already used the first element, so we go one number to the right, and because we have used last, we go one number to the left. And then we simply just output the sets here, okay? So let's see why this strategy works, okay? If we look at the specific scenarios here, where n has these values here, this is the sequence of the numbers, and these are the sums essentially. First of all, let's look at the cases where the sums are odd numbers, okay? So for n being equal to 5 and n being equal to 6, the sum is an odd number. So for these cases, we have no solution, okay? So we're not gonna look at any strategy for these two cases, since we already know that they don't work. But for n being equal to 4, actually for this case as well, for n being equal to 2, we also have no strategy with a sum of 3. Now let's look at the case where n equals to 4 and n equals to 7 individually. So in the first case where n equals to 4, our strategy here will go on and let's use orange for the first group. So set A, I'm going to use orange, and let's use pink for or purple for the second group, okay? So the strategy here goes like this. So if the first number is odd, we're going to push to the first set. So in this case, the first number is odd, so we're pushing number 1 and number 4, which is the last number, to the first set. And then in the next iteration, the first number will be even, okay, since we increase it by 1. And thus we will push to the second set, okay? Now, for the case of n being equal to 7, as I said, we use numbers 1, 2, and 3 to make the sets have equal sums initially. And because n minus 3 will be even, and n minus 3 divided by 2 will also be even, so we're going to have an even amount of pairs essentially, we will enforce the same strategy, okay? So for this case, for n being equal to 7, again, we use 1 and 2, and then 3 to make n to have essentially n minus 3 numbers now, okay? So now sets A and B, they have equal sums, and that sum is equal to 3. So now again, the first number now is an even number. So I will take the first number, which is 4 now, because I have set this here, and 7, which is the last number, and I will put those in the second set. Then, after I increase first, the number that it is pointing to is an odd number, so 5 here, and the last number will be pointing to 6 now. So I push those two into set A, okay? And if you observe, you will see that the sum is always 14 for both cases. Okay, so let's look at a bigger case here, okay? So for, let me just fix the sums here. So let's look at for 11, okay? So for 11, the sum will be equal to 66, okay? So from 1 up until 11, the sum is 66. So it should, based on our code here, we're going to the case where we say, yes, we can do the division, okay? And again, we're gonna follow this strategy. So I'm just gonna implement the solution here. So 1, 2 will be added to the first group, and then 3 will be added to the second group, okay? Then 4 is even, so we add this into the second group, and the last is 11, so we add this also to the second group. Then for the next number, which is 5 and 10, we add them to the first group, then 6 and 9 to the second group, and then lastly 7 and 8 to the first group, okay? And if you look at this, we have a balanced amount of pairs, okay? So this is one pair for the first group, and 5 and 10 is another pair. So essentially we have two pairs which have this sum of 4 plus 11 essentially. And again, for the second group, we have this pair here, so 6 and 9, and then 4 and 11. Okay, so two pairs for every group. And if we keep going this you can test this for greater numbers as well, this will be true. But now let me prove why, for the case of an odd number, n minus 3 will be divided by 2, okay? And why will the case be the same for an even n, not for n minus 3, but for n in the case of an even number? Why will the amount of pairs be even, okay? And that's allowing us to do this strategy. So initially I'm going to use this formula here, the sum formula, okay? So as we said, this sum is even. So n times n plus 1 divided by 2 is equal to 2 times some integer number. Let's call that number x, okay? So it is even, okay? Now, this can be written as n squared plus n, okay? Divided by 2 equals to 2 times x, okay? We can remove actually we can remove these 2 here and make this a 4, okay? So if we write this, n squared plus n equals 4 times x. So we know that n squared plus n will actually be divisible by 4, okay? So let's prove now that n minus 3 will be divisible by 4 as well. So if n minus 3 is divisible by 4, then we have an even amount of pairs, essentially, okay? That's what we're trying to prove here. So let's replace this n here with something that shows that this is an odd number. Okay, so we are looking at the case where n is odd. Okay, so for n is odd, let me just use green here. So let's say that n equals to 2 times y, so another integer here, plus 1. Okay, so 2 times y plus 1 gives us an odd number essentially. Okay, now let's move on to our proof here. So n squared will give us 2y plus 1 squared plus 2y plus 1 equals to 4 times x, and this will give us 4y squared plus 4y plus 1 plus 2y plus 1 equals to 4 times x. Okay, and now if we move all the numbers that have the 4 factor here in the front, we will see that 2y plus 2 equals to minus 4y squared minus 4y plus 4x. Okay, now if we remove 4 from here, so if we go 2y, so minus 4, this will be 2y minus 2 equals to minus 4y squared minus 4y plus 4x, and now we add the minus 4 here, so minus 4, because we have already had a minus 4 in the left hand side, so we have a minus 4 in the right hand side. Okay, so there is no doubt that this part here now is divisible by 4, and thus is the left part. But if we look at the left part, this actually, and the equation we declared here, because n was an odd number, we can see that n minus 3 essentially, n minus 3 equals to 2y minus 2, okay, which is exactly what we have here. Okay, so n minus 3 is proven that it will be divisible by 4. Okay, now let's look at the case where the n is actually even. Okay, so again we have the same formula for the sum here. Okay, so the same equation is true. So n squared plus n equals to 4 times x. Okay, so this equation is still true, but n now is being even, so n equals to 2y this time. Okay, so if we replace this into our equation, we're going to have 2y squared plus 2y equals 4 times x. Okay, and 2y squared will give us essentially 4y squared plus 2y. Okay, and times equals to 4 times x. Now let's isolate the ones that have a factor of 4 in front of them. So 4 times x minus 4y squared, okay, equals to 2y, pardon me. So 2y equals to 4 times x minus 4y squared. Now, what will n? So what we're trying to prove essentially in the case of we have an even n. Okay, so in this case here, okay, so n equals to 2y. We want to prove that this number will also be divisible by 4. Okay, so that if we look at the strategy we used here, so for example for number 4, okay, which is obviously divisible by 4, we're going to have an even amount of pairs. So 1 pair here and 1 pair here. Okay, so now the proof is that n will be so 2 times y essentially in this case will be divisible by 4. So if the right hand side is divisible by 4, because everybody has a number 4 as a factor here, and x and y are integers, it means that also n is divisible by 4. Okay, and having proved those two properties here for the two cases, we can go ahead and implement a solution which proposes the strategy of splitting the sequence into pairs of into pairs that have the same equal sum. Okay. So that's pretty much the solution for this problem. I hope this helped you if you got stuck in the process of solving this. If you did, please leave the video a like, subscribe to the channel, and I will see you in the next one. Goodbye.